Hi everyone. Good afternoon. So my name is Abinaya. So I have with me Gyan, Ranjan, and Amit. I think is not able to join us. So we work for Neuron7.ai, and we are a service intelligence platform. So the paper that we would be presenting today is about unsupervised named entity recognition for the high-tech domain. So before we go into the details of the paper, a brief introduction of Neuron 7 and what we do and why this paper as a concept is very important. So Neuron 7 is a service intelligence platform, like I told you. So we serve different domains such as the high-tech domain, the technology domain, the medical device manufacturing domain, and several other domains as well. So what we try to achieve as a product is that for many of these domains, we try to preemptively identify what was the the technical problem that has occurred in a particular device, or any based on the domain, the entity on which we are performing this would differ. But since we'll be discussing about the high-tech domain, we'll be talking about different devices and products. So for example, let's assume like if it is a phone, or if it is a simple computer or any other technical appliance that will be purchased. So the service intelligence platform try to identify what the customer is trying to is facing an issue with. So for example, sometime the customer might be saying that my display has gone out. So we try to understand what is the information that has been provided, and also sometimes based on different trends that has been shared by similar devices or similar like symptoms, we try to preemptively identify what are the associated errors that could come, so that the agent, the technician, on-site technician, can try to solve the existing problem and also preemptively predict that what, this is something that you'll be facing since display is gone out. Next is possibly battery, and accordingly you should be able to do this steps also to prevent that. So sort of a preventive maintenance as well. So for this, as you can see, we deal with a lot of natural language processing, and most of the information that we'll be dealing with is plain English combined with a lot of business language. So for example, people will be talking about the errors that they'll be facing, and the model numbers that they have purchased, or the versions, or different parts that they are facing the issue with. So in this case, we can see why it is very important for us to identify what are the specific entities that is being discussed. For example, what was the part that failed? What was the test that was failed? Or what was the error that the symptom that the machine has shown? So this is where named entity recognition as a problem comes into picture for us. So since we would like to assess the technicians, the most important aspect of it is to help them understand the customer complaint. Sometimes it tends to be very long and very wordy. So the platform tries to predict which is the most informative content, and from that we try to extract entities which would help the technician understand and handle it accordingly. So for the scope of this paper, what we have tried is named entity recognition as a domain has been solved in the NLP area, but often we see that they've been trained for very generic entity types, such as what was the name of the person, or the location, or the time frame, and all that. But since we are dealing with real-time business data, the data tends to be a bit more messy, and the actual information that is present might be very condensed in a very long textual block. So these make it very, and also there's a dearth of availability of annotated data for different business domains. For example, if you go for high tech, we don't have at all any open source data that has been available, and even if it is open source, products will be changing, and similarly the errors that is faced in a particular subdomain of high tech will be different, which is why we want to solve this problem by first focusing on a data generation pipeline. So what this pipeline should be doing is the model should be able to identify what are the most prominently available and also the minority class of entities, And since this will be further used to train our entity recognizer using different deep learning approaches, such as, once we have annotated data, we have BERT models or Electra models or Roberta models to fine tune the architecture to, extract entities. So the model should be in such a way with minimum noise, so that it can be used to fine tune downstream tasks for several niches. And like I told earlier, the fine tune model should be, having the ability to learn all the latent patterns and also to generalize it on unseen data. So this is the reason why we got into it. And in this approach, what we have used is we have used several fine-tuned and pre-trained models, such as question answering or natural language inference, or we have also used sequence-to-sequence models to try to generate the data and subsequently reduce the noise of the data. And then we have also shown how our model is better in terms of performance by comparing, their corresponding performances. So a sample illustration of what I'm trying to say. For example, you see in the first case, if someone is saying that, the display was black all of a sudden, the model failed some tests, test 1 and test 2. So here you see that the display is a part that the user is talking about, and there are a few functional tests that has failed, such as test 1 and test 2. So similarly, we have been dealing with this kind of data for a while. So we, also have a lot of business knowledge from the actual agents who consume this data. So we sat with them, and we also try to identify what are the different entity types for which we should be doing this exercise, so that it would help them in the best way possible. So based on that, we have, identified a few entity types, such as the parts that is present, model number, error that is exhibited by the device, and the test that the device has failed. So are there any questions so far?
No, go ahead, please.
Okay, sure.
Ask in the end of the session.
Okay, sure. So moving on into the pipeline that we have used. So we are not, going to go into the details of how a transformer has been built, because most of the focus of this paper has been towards the sort of the stage before the model training, where, we try to use different question answering models and NLA inference models to generate the data. So the first stage that we would be focusing, the main component of the pipeline, is data generation. So that is corresponding of 3 main blocks. So the first block is for, so this is all unstructured data that we have initially. So, we have a lot of notes that has been written by the technicians based on their site visit. They would have gone through and seen that, the device didn't do this, the device didn't exhibit this symptom and all that. So once we have this unstructured data, as I discussed earlier, we also have several entity types that we would like to extract. So the first knowledge context that we provide is the question that corresponds to each entity. So what do I mean by that is, for each of the entity, there is a way in which we can formulate it as a question. For example, if we would like to extract the part numbers, so we can ask a question such as, what was the part number, that was replaced, or what part was replaced, or what is the part number that the user is talking about. There are multiple such knowledge contexts that can be provided to each of this entity type. So we experimented with several of these questions, and then we compared the performance of the question answering model. So the performance here was how many extractions is possible, and also what is the probability or the confidence with which the model is able to predict. So based on that, the first stage of candidate entities has been extracted for the unstructured data that we have. But the challenge that we faced here is that Squad, as a data set, is on very generic data, such as the paraphrasing data that is about general English, right? Like, the president is here, where did the president go? Or very colloquial, or it's very lexically nicely put. So that is why there's a lot of margin for error when there is a business context that is present. For example, like I had told earlier, if someone is talking about a specific test, how do you know that this is the only thing that you should be extracting? This is where we have a sequence to sequence model that in conjecture with the data Squad model reduces the noise further. So what do we mean by that is, since there is no domain knowledge that has been injected until this stage, we add another business context for each of this entity type. So what do I mean by that is, for example, if you're trying to extract the frequency, that was measured. So we try to add a business definition, such as, frequency is the rate at which current changes, or frequency is measured in hertz. Whereas if you want to measure amplitude, we say that amplitude is measured in decibels. And also for the replaced parts, I can say that, a part is a part of the device which should be, this way, it should follow these patterns. So we train our sequence to sequence model in such a way that, first, given a question, given a business context, which would be the definitions for each of the entity type, and the answer that has been generated. So for example, I would say that functional test should be this, and I say that, in this above context, that the model has failed, or the model has failed test 1 and 2. Is this a functional test? Does this confine to the definition of functional test that we have provided? So this is the whole reason for this model. The model has been trained to identify if a generated answer confines to the business definition. And based on this approach, we could reduce a lot of noise on, all the majority classes, because we had a lot of, for a few classes, we had a few data points which could help us reach this. So once we did this, the data was a bit noise free, and we could also identify that, okay, so in this particular agent nodes, we could extract 100x entities and stuff. So the third stage is where we could not we could not procure a lot of data for a few entity types. For example, there might be very specific amount of entities, such as the model numbers or the model names. We might not have a lot of examples where they are present in different variants. So we used a lot of business rules for this. For example, a model number should be following this pattern, or there should be this context in which it is occurring around. And based on this, we try to populate the minority class entities. So now all these three methods combined, we could reach at a set of annotated data, which was, for each agent nodes, what was the entity that is present, and what was the start of it and the end of it, and what was the entity type that they belong to. So for our assumption, we didn't use any sort of overlapping entities, as in if there is a token that is assigned to, let's assume, functional test, it didn't make any sense for us to also tag it to another entity type, which is why this data format was very, similar to ConLL or any other entity recognition data that we have out there. So once we have this model, we try to use the transformer based embedding architectures. So we used, the embeddings that we could extract from three different approaches. One was the BERT based model, and then the Roberta based model, and the discriminator part of the Electra based model. So once we have these embeddings, we also wanted to account for the non-linearity of the data, and to, try to find more latent features, which is why instead of using a simple softmax, we try to use a few other fully connected layers. And also with a ReLU unit, we try to find what was the entity that we could find, what was the entity that we could be training for. So the laws that we used was categorical cross entropy, and this architecture, is the architecture remains the same, only the embedding that we extracted was differing from either a Roberta or a BERT or an Electra discriminator, like I had to. So moving on into the model performances, we found that the cross entropy loss of, the BERT and Electra model was, it was decreasing, it was learning, but we could see that after 15 epochs, the model was, not reaching a very flat, steep decrease. It had started to flatten. Wherever when we see the Roberta model, the model was training nicely, and it could also generalize on the other various classes that we had trained the model for. So as you can see here, even if so I have also mentioned all the different entity types for which we wanted to train: frequency, amplitude, parts, test error, and model number. So many actually in this, the error code and model number are the minority classes. There were not a lot of data for this. This is why you see that the BERT and Electra, they were doing very good on the trained sample, but on the valid, it was not doing very great. However, if you look at the Roberta, it was consistent on both of this train and valid sample, which is why, and also on the majority classes as well. So this is the final model that we have deployed in our application as well. And it has helped us identify the entities to reasonably good performance, in such cases. So in conclusion, what we have tried to achieve using this paper is we have got a system that generically generates data in a domain and agnostic manner. So we have tested with a high-tech domain, and we've also tested with a few other domains, since there is no, in the process, there is not a lot of domain specific information. We can also use this for different domains if the data is appropriate. And we've also found that which model works the best for our use case and how it also generalizes for various classes. So in the future work, what we would like to do is, now for this paper, we have only focused on the data generation techniques and how to, reduce the noise that has been generated in the data. We would also want to look at a few zero-shot and few-shot learning approaches, so that even if the the data has been generated, and how do we also leverage the models in such a way that the performance is not impacted by the dearth of data. And we would also like to incorporate several active learning mechanisms to incorporate user feedback and keep increasing the data pool that is available for the model training. So that was a brief overview of what we have done. Any questions so far? I mean, yeah.